If you've ever rolled around hard balls in your hand, you may have noticed a distinct sound. They chirp. If I put them on a soft surface like my lab bench, they do it even longer and more distinct. I'm going to be figuring out the mystery of the chirping balls and seeing if I can make the longest ball chirp ever recorded. And we'll see some amazingly beautiful geometric patterns that arise out of a simple act of knocking hard things together. If you've ever put away glassware, like these glass cups here, you've probably heard this same chirping sound. A chirp is different from a simple ding because its frequency rises. It starts at a lower pitch and then sweeps up until you can't hear it anymore. For example, this is a chirp. The question is, what's increasing in frequency? Are the balls vibrating when we knock them together like a tuning fork that's making the sound? Well, I don't think so, because that would make a constant frequency, but we hear an increase in frequency. So what could it be? I want to know if they're actually separating and coming back together thousands of times to make this frequency. So I need something physical that will tell me if they're separated or not. Even a slow motion camera won't work in this case because the distance that they separate and hit each other is microscopically small. So I have a better way to try this. I'm going to connect them to a DC voltage in series with a 200 ohm resistor. Then I'm going to measure the voltage across the resistor. When the balls are in contact, the voltage will just be given by V equals the resistance times the current flowing through. But when they aren't in contact, the voltage will be 0 across the resistor, since there's no current flowing. So when they touch, we get around -14 volts. So if this works right, I should be able to measure when the balls are touching versus when they're separated. But I can't use a regular voltmeter for this because the collisions are going to happen too fast. So I'm going to measure it with my oscilloscope. So I'll just hook up my probe now. Let's see what we get. But before we continue, I want to tell you about the sponsor for this video, Lien. They sent me their new Lien Pick Kit S1, and I've been using it all week to organize my house, print pictures, and just have fun. The Pick Kit S1 uses a high-precision thermal print head. The printer heats different layers in the paper to create the image. Then a tiny internal blade automatically cuts out the shape for you. The setup was super easy and took only about a minute. You just plug it in, load the paper, open the app, and you're ready. It connects straight to your phone through the Lien app. And what's really cool is the new AI Smart Cut and AI Auto Subject Selection inside the app. You just upload a photo and the AI instantly finds the main subject and removes the background. And then it creates the perfect cut outline for you, no Photoshop required. We used the Lien Pick Kit S1 to make labels for toy bins, backpacks, lunch boxes, chargers, and even little character stickers my kids drew themselves. They tap the picture in the app and the AI outlines it and the printer cuts it. No scissors and no mess. Also, you can use the AI Lab in the app to create different style cartoon versions of whatever pictures you take. Here's a cartoon version of the same sticker I printed earlier. This is so cool. Right now they're having their biggest sale of the year with a 20% discount. So if you want to try out the Lien Pick Kit S1, you can click the link in the description. And now let's get back to our experiment. So when I just touch them together, you can see that little spikes show up on the oscilloscope. But we can't really tell what's happening because it's refreshing. So I'm going to record just one knocking event and we'll look at the whole recording of that event. And look at what we see. We were right. You can see that we see a sharp spike in the voltage every time the balls are touching together. But over a span of about 200 milliseconds, we get a bunch of spikes. I recorded this multiple times and I found it ranged from about 30 to 60 spikes. It's so crazy to think that they were actually physically coming apart and then hitting back together enough to measure the voltage change between them. So there was physically a current going through them and then they separated enough to not go through them. So they're actually physically knocking together that many times per second. And I can see how many times per second they're knocking together by zooming in on this graph here. And at the last, around every 2 milliseconds, they're knocking together 3 times. That's about 1500 hertz. But notice that there's a specific pattern to how they knock together. They seem to have a non-linear decrease in their time between hits. If I graph the time between collisions, it looks like this. So we get an exponential chirp, not a linear chirp. To understand this, let's dissect what's going on here. If I push the balls together with a constant force, then they'll hit with some initial velocity and then rebound. Now, still balls are actually really elastic, If something's perfectly elastic, it will bounce off with the same velocity that it had going in, but just going in the opposite direction. The ratio of the incoming velocity versus the outgoing velocity is called its coefficient of restitution, or COR. COR equals 1 for perfectly elastic materials. Steel on steel is very close to this. It's about 0.95. If we look at the time it takes between collisions versus the velocity, we get this beautiful geometric progression that eventually converges. The area of these squares represents the distance the balls move apart, so you can see that it also gets smaller and smaller. What's really neat is that we can change the coefficient of restitution by putting them on different surfaces that give us an even higher coefficient of restitution. And I found out I could get it to last the longest by putting it on this spandex sheet that I used for one of my videos. Now let's measure the voltage on the balls again on this spandex sheet, and we see that we still get the same pattern. So we can see that we get the exact same pattern, but just with a lot more collisions. I'm getting about 8 times the number of collisions by increasing the coefficient by just a few percent. What's really cool is that through all these setups, they follow the same pattern of exponential chirping, and they always end at about the same frequency. It's always around 3 hits per 2 milliseconds. So I'm guessing this ending frequency happens because this means at some point the recoil velocity is so slow that the balls just stick together and don't actually separate. So if I graph the time between collisions, and I find that the minimum time between collisions is about 2 milliseconds before they start sticking together. So you can see how no matter my coefficient of restitution, eventually I always hit that maximum frequency. But what does change is the number of hits it takes to get there. So on spandex, I hear a lot of hits and it lasts a long time, but eventually it gets to that maximum frequency or minimum rebound velocity before they stick together. And what's really cool, just to finally show that it really is collisions making the chirping sound, I'm going to record a ping pong ball hitting against the table. And then I'll put it in Adobe and increase the speed and listen to what this sounds like. It's the exact same chirp sound as the balls colliding. They follow the same amplitude decay, just at different speeds. So it really is collisions happening microscopically and really fast. And I bet this has been the most in-depth analysis you'll ever see of colliding balls. And thanks for watching another episode of the Action Lab. I hope you learned something. If you haven't subscribed to my channel yet, remember to hit that subscribe button, and we'll see you next time.